So slowly and steadily, we are kind of easing into the notation in chapter 3, I hope. So by problem 3.6, if you have solved problems 3.1 to 3.5, you probably have a pretty good idea of the connection between the survival function and the mortality rate. So that connection looks like this, and it is what we will use to show that the survival function is given by this expression here. So let's just start. So let t be greater than 0. Then we are all set to use our formula here. Then the survival function is equal to the exponential of minus 0 to t, so the integral from 0 to t of the mortality rate. And let's just evaluate this integral on its own, so we don't need to write up this first part each time we go on to a new calculation. So where the integral of the mortality rate is given by the integral from 0 to t of beta times alpha to the minus beta times t to the beta minus 1 dt. And since I'm integrating up to t, it's probably a pretty bad idea that I have t inside the integral as well, so I just take s to the beta minus 1 and ds. Now, one of the things that I just noticed here vaguely is alpha and beta are both greater than 0, so I can never risk s to the minus first inside here, which is pretty nice, because if I had s to the minus first, then I would need to make a special case where the antiderivative is log of s. But I don't have that because beta is greater than 0, so I can just do this the good old-fashioned way. I have alpha to the minus beta out here, I have beta out here as well, both are constant, and then inside I have s to the beta minus 1, which after I find the antiderivative of that, that is given by 1 over beta to the multiplied by s to the beta, evaluated in t minus this evaluated in 0. So the term where I evaluate in 0, it just vanishes because I have 0 here. So I only have the first term with t, where I have beta over beta times alpha to the minus beta times t to the beta. Let me see, is this all working out? Well, this is all working out pretty fine. That's nice, because then the betas, they go out, and what I have here is t divided by alpha to the beta. Hence, the survival function is given by e to the minus and then t divided by alpha to the beta. Was that what we wanted to show? Well, yes, that was what we wanted to show. We wanted to show that the survival function is given by exactly this expression up here. So now we have done part 1. Let's go on to part 2, which is to show that mu is increasing for beta greater than 1 and decreasing for beta smaller than 1, and that the Weibull law equals the exponential law for beta equal to 1. So let's just take that one step at a time. How do I do this? What's the best way to do this? You know what? Since we're not going to really need this part anyways, I'll just delete that and we can just continue here. Okay, so let's just start for beta equal to 1. So when beta is equal to 1, so when beta equals 1, we have that the mortality rate is equal to, well, 1 multiplied by alpha to the minus first multiplied by t to the zeroth. So mu of t is just equal to alpha for all t greater than 0. And this means the mortality rate is constant. So here we have the mortality rate of the exponential law. So here we have the mortality rate of the exponential law, because it was exactly the exponential law where the mortality rate was constant, which yielded a memoryless distribution. So look at exercise 3.5 if you just need to freshen up on that. So now we also want to show that the mortality rate is increasing for beta greater than 1 and decreasing for beta less than 1. So in order to do that, let's just say, well, let beta be different from 1. Well, if it is different from 1 and still greater than 0, that's implicit here, then the derivative of the mortality rate, well, it's given by beta multiplied by alpha to the minus beta, and this entire thing is still greater than 0 per assumption. And what we then have is we take the beta minus 1 down here and multiply by t to the beta minus 2. And what we see here is this thing here is also positive in lieu of t being positive. So the only sign that can affect the sign of the derivative is, well, the sign of the beta minus 1. So we see if beta is greater than 1, then beta minus 1 is greater than 0, hence mu of t, hence mu has a positive derivative for all t, so hence mu will increase. Will be increasing is probably a better way to say that. Will be increasing. Now, if beta is strictly less than 1, then we can see that the beta minus 1 part will be strictly less than 0, whereby the derivative is negative, and we can say hence mu will be decreasing. Probably is decreasing is a better way to write it. Doesn't really matter too much anyways, but yeah. So now we've shown that part as well. We've shown that if beta is greater than 1, then the mortality rate is increasing, in which case, good for life insurance. It's good to model life insurance, where age means worse chances of survival, kind of. And if beta is less than 1, then the mortality rate will be decreasing, which means, well, good for claims insurance, like in non-life, or high infant mortality. So it can work in certain different setups. The last part in this exercise will be to calculate the conditional probability of survival. That will be in the next video, so see you there.